Okay, so we're into 1.7, and really, again, Chapter 1 is an exploration of review of last year's Functions 11. And Chapter 2 gets more interesting with rate of change and pretty much leads directly into calculus. In this chapter, it's really exploring operations with functions. It's looking at combined functions, which is something you reviewed last year. And it's probably more accurate to scientific systems that are complex because you're going to have several functions that are combined or overlapping. And to model them is difficult. So this one, they show a coffee house that sells a hot coffee and a cold coffee, and shows which temperatures of the day dictate how many cold coffees they sell, and which temperatures of the day dictate how much hot coffee they sell. Obviously, when it's cold, they sell more hot. When it's hot, they sell more cold. And then they're trying to say, essentially, when is the best? When is your biggest profit? Okay. Now, both are lines. They're both line functions. This is the cold coffee, and this is the hot coffee. So obviously the hot coffee is declining, and they just are asking you basic questions of like, what does it mean when you add them? So that would be looking at your overall sales. I believe this represents the number of so the y-axis is the number of coffees sold. So what does combining them mean? It would mean the total coffees you sell in a day, in any particular day. And as the day gets hot, of course, they're going to inversely affect each other. And what does one subtracting the other mean? And that's a good question. That would be the difference in coffees you sell based on temperature. And it might be a good one to examine to sort of say which coffee should you sell based on the temperature that's sort of in the middle. Obviously, a really cold day, you're going to sell more hot coffees. And a really hot day, you're going to sell more cold. But this would answer the question, on those medium temperature days, what's the most profitable drink to sell? And then they ask you to study it. Desmos is great here. Explain how the sum function would be different if they were both increasing or both decreasing, which means you're essentially selling a drink that goes down as the temperature goes up or goes up as the temperature goes up, which just means you're going to sell more and more drinks the hotter it gets or the colder it gets, depending whether it's decreasing or increasing. The increasing ones would sell more and more as the temperature goes up, and the decreasing would sell more and more as the temperature goes down. What does that represent? We sort of answered it. What does that represent? We sort of answered it. And it's good when you can just throw these graphs and then they just review. And it's good when you can just throw these graphs on Desmos and see what happens. So let's have a look. We got 3x plus 10 and minus 5x plus 200. I think it was. Yeah. Okay, and if you look at them individually, there's the blue one, and this is a really good indication of on that day when they meet, they will be both selling equal drinks. So on that day, you should sell either hot or cold. But when you're on this side of it, you can see you're selling less and less hot drinks and more cold drinks. So this side, you're going to make much more money selling your cold drinks. Now keep in mind, I believe, did they throw the price in there? What would have been really interesting? Oh yeah, that's what the 3 and the 4 means. No, what would be really interesting is if you had the multiplier in here. So to show you your total profit. So for instance, if this is your cold drinks, you would multiply the whole thing by 3. And if this is your hot drinks and you're making $4 a hot drink, it also depends what your profit is, but let's assume that's just pure profit. Then that really changes the story about when you should switch drinks. And you might say, well, why switch drinks? Why not sell both? It could be that you can generate more focusing on cold drinks if you can make more of them faster, right? So the staff wasting time, let's say you look way down here when it approaches zeros, that staff wasting time making that one drink here could be making a cold drink way up here, and it would be more money. But let's just go back to what they've given us and just assume that that's sort of like profit. We're going to do an h of x and we're going to add them. Plus a g of x. Sorry, my fingers are going off, and we're going to turn off the old ones. So this one shows you that when it's 0 degrees out, you're selling a total of 210 drinks. And as the temperature goes up, you're selling fewer and fewer drinks. This is where the profit model would be more interesting, because then you can see which day you're going to make more money, which drink you should sell. But you can see that the total drinks here on this day, when the day is 105 degrees out, they're essentially not selling any drinks. So at 105, sorry, that's not true. They're selling an equal amount of hot and cold drinks. That's because we're adding it together. Okay, so on that day, yeah, they're selling, the total is 0. So there's negative hot drinks going on there and positive cold drinks. So at 105, and actually we should technically go back and look at these graphs, and technically you should limit the domain for when you're actually selling cold drinks versus the domain when you're stop selling hot drinks. For instance, we should not be including anything in the blue line after this, because you can't sell negative drinks, right? You can't sell negative drinks. So the domain of this should stop at 40. Technically, if you want a good idea, and I know the textbook isn't doing this, but if you wanted a good scientific idea of where your profit line, you should stop that at 40. And since sky's the limit on cold drinks, you would only stop that at 0. Or even, yeah, below 0, right here. You'd stop it at minus 0.33, because you're still selling positive cold drinks on that day. You get a 3.33, a smaller than x. Or sorry, bigger than x. And I won't want to put it there. I want to put it on the cold drinks. All right. Didn't quite get it. 2.33. And that's because anything below that is selling negative drinks. So in my opinion, this is a far more accurate look at what temperatures you are. What's interesting about this? Oh, there we go. So it's saying that, at this point you wouldn't add them up anymore because you're getting into negative territory. But it's interesting, and let's include the x's so that we can have it in there. There we go. So that means at 40 degrees, you're selling a total of 127 drinks, and that's after that. You should just be, notice it doesn't add anything after that, and we should be seeing a bounce back of the cold drinks at that point. So from this point on, you should also add a function showing the cold drinks, because we're dismissing the hot drinks. But the problem is when you add functions, it's only going to include the smallest range. So it's stopping at 40, and it's not showing what happens. Essentially, you'll see this same line bounce back onward. So if I was going to put, again, a more accurate reflection, I would put the f of x line again, but I would, in this one, just show x bigger than 40. And that gives you a really good idea of the total number of drinks you sell, because here the hot drinks are dragging us down, and then boom, after we stop going in a negative version of hot drinks, we're up here and we're starting to boom on the cold drinks, and based on temperature. See, let's say you only ever get up to, let's say this is Celsius, and let's say you only ever get up to 100 degrees. There. You could sell as many as 306 drinks because you stop selling the hot drinks. So that's a really complicated thing I did. But let's just look at what they intended for. They didn't put any of the limits on the range. On the domain, rather, sorry. And technically you should. And if you don't, you can see this line just goes through right there, and you'd be tempted to dismiss everything after this, which wouldn't be too unreasonable because it's 103 degrees out. I just don't find it's that accurate a portrayal of what's going on. because they're subtracting negative hot drinks in this graph. But let's look at the opposite, y of x, when we subtract the two functions. So you do f of x minus g of x, which means what? How many different drinks from cold to hot? What's the difference? So right here, there's 24, at 24 degrees, there's no difference in them. And then as you go up here, you're selling 55 more cold drinks, you're selling 99 more cold drinks, you're selling 148 more cold drinks, etc. You can do that again this way, which would be subtracting the cold drinks, that's hot drinks, minus the cold drinks you sell. And you should see that an opposite line. And if you look at that, this is how many more hot drinks you sell, that's how many more hot drinks you sell, that's how many more hot drinks you sell, and then it stops. Because you can't sell negative hot drinks, and you can have negative temperature. So as it gets colder and colder and colder, you can see that, I shouldn't have stopped that other one at 0. As it gets colder and colder and colder, you can see you sell many more hot drinks. And it's the difference of number of drinks you're selling, depending whether you subtract hot from cold or cold from hot. You can see analysis can go deeper and deeper and deeper and deeper, depending on what your temperature ranges are, what you're trying to measure. If we add price into this, we'll get a curious idea of what our most profitable situation is. Now, and that's probably a day you should hire more staff. Now, keep in mind, business models do this, but they add like 20 products, and they look at and see, they even see if we go over 20 products, are we wasting resources? Because most good restaurants won't have too many things on the menu because your kitchen would be full of ingredients that go bad. So you can see that this sort of thing is a very good business analytical tool, and if you're a smart business, you're doing these modeling all the time. Anyway, let's go straight into it. So here they give you a bunch of a function that's coordinates, and then they give you a function that's coordinates, and they ask you to add them. And in this case, what you do is wherever you see matching -4, and actually you can do it without, you would add their y's. So here, if we're adding them at -4, you add this, we get 6, 2 plus 4. If you're subtracting them, you would take, if you're doing f minus g, you would take 4 minus 2. So you get -4 comma 2 for this one, and you get -4 comma 6 for this one. If we reverse that and subtract g, so essentially you're always keeping the same x. The x doesn't change. What you're subtracting is the y values. And so when we subtract this one, we do 2 minus 4, we get -2 for this one. And then when you multiply them, that's a whole different thing. You might say, what happens in a function? When would you ever multiply a function? It would usually be something that's growth. Let's say you have frogs eating insects, and the more insects there are, the more frogs there are. And you can provide endless insects, and you want to determine how many frogs you could farm. It would be something like that. It would be essentially my production gets multiplied by some other factor. But they're just teaching you. So what would you do for f of g? You'd keep the -4 here, and you'd take the y values, and 2 times 4 is 8. And you keep doing that for all the x values that match. And you're going to encounter situations for this, for instance, this one has a 0. And there is no coordinate for f, and you'd be tempted to do this calculation using 0, 0 for the f value, but there is no value for f. These are very fixed coordinates. Therefore, for 0, 2, you would ignore it. So you're just looking for coordinates here that have a matching x, and then you're only doing this multiplier for the y value. Let's see. I don't know if it does matching points. Let's see if it will. I think you can do a table, but no, I don't think Desmos will let you do matching points. But if you want to see it in writing, because sometimes people don't absorb in words, you would do this, okay? So focus on one thing at a time. So we're going to focus on adding our f of g's. We're going to add our f of x's and our g of x's. We're not going to focus on the others yet. And then we're going to only take the values that have common x values for f and common g values. You might say, what do I do with that 0, 2, and the g value if there's no matching What do I do with this one? Yeah, in this specific situation, it's not relevant. It's it doesn't have anything to multiply. And you might say, well, again, isn't it 0, 0? No, because 0, 0 would be on that data set then. So you can't multiply by 0. You shouldn't be subtracting 0. You shouldn't be taking 0 minus this. And you shouldn't be multiplying with anything. So for that data set, because there's no common x comparison, you shouldn't be using it. And same for this one. Notice there's a 2 on this one. There's no 2 on this one. Notice there's a 3 on this one. There's no 3 on that one. So it'd be tempting to include it, but in my mathematical opinion, you wouldn't do it. So then you would rewrite their x value. So let's start with this one. So they share the same x value, so that means that minus 4, if I'm adding them, I'm going to add their y values. I'd get 6. And then we're going to focus on this one. At minus 2, because they share the same x value, we add 4 and 1. We get 5. At 1x, I get 1. You're not adding the x's, and then you add the y's, 5. And then at 4 and 4, we're going to add the y values, and I get 4 comma 10. And then I plot this, and this is my new graph of f plus g. So this would be f of x plus g of x. And then it would equal that. And that's my new domain, and that's my new range. Okay? So that's what you do with fixed figures. And it might seem counterintuitive, but it makes perfect sense because the only data sets you can compare are x values they share. Let's look at the next one. Okay, this time you're going to take all the y values of f and you're going to subtract the y values of g. So I'm going to take the same minus 4 and I'm going to do 4 minus 2 because it's f minus g, 2. And then I'm going to take minus 2 and I'm going to take 4 minus 1, 3. And then I'm going to take 1 and I'm going to take 3 minus 2, 1. And then I'm going to take 4. I'm going to do 4. And what's 6 minus 4? 2. And here's my new data sets. Minus 4 comma 2, minus 2 comma 3, 1 comma 1, 4 comma 2. And that's f minus g. You might be tempted to say, well, g minus f will be the same thing. Not true at all. Not true at all. And to show you, I'm just going to put the data sets in different orders. So I'm going to put this one below this one and put them together. So I'm going to start with minus 4x still. And then I'm going to do 2 minus 4. Get minus 2. I'm going to take minus 2 and I get 1 minus 4 minus 3. You can see they're very different. Then I'm going to take x value of 1 and I'm going to do 2 minus 3 minus 1. And then finally I'm going to take the 4x value. I'm going to take 4 minus 6 and I get a minus 2 again. Notice that these still share the same y coordinates, and that's because when you add them, they'll share the same y coordinates. They essentially had very similar y coordinates, or very similar differences between their y coordinates, I should say. And there we go. That's my new data set for that. And this is no different. You simply multiply the y's and the x's. So looking at f times g, f times g. I do the same x values, minus 4, minus 2, 1, and 4. And only this time I'm going to multiply 2 times 4, 8. 1 times 4, comma 1, comma 4 rather. 2 times 3, 1, comma 6. And 4 times 6, 4, comma 24. And that's my new data sets for f times g. Now notice, you'd be tempted to multiply all the numbers or subtract all the numbers, but no, they have to share x. That's why x is an independent variable. It's not affected by these things. What you're trying to determine is the new y. Then they go on and they show you very similar things. Before I do then they ask you to do the same with graphs. Okay, very similar process. Except for the graphs, what you have to do is you plot all the same x values, so you can see that they have all the way from minus 4 all the way up to 1. Okay, so that means they have x values all the way through that. It's including the last dots. There's a plus, so you do indeed add the last dots. And then you just have to find the y value. So here I have minus 4, comma 1, and minus 4, comma 2. And I'm asked to add them. So I get minus 4. What's 2 plus 1? 3. I'll do it in green. So 2 plus 1 on the y's is that. And then you can even go to the last dot and say, okay, I got 1 comma 2 and 1 comma 6, so I'm going to do 1 comma 8, and it's right up here. And because they're straight lines, you almost automatically know they're going to connect. But if you needed, if your teacher wanted to see at least 3 coordinate spots, you would go to the next line here, minus 3. So minus 3, I have a little bit above 1, a little bit below 2. So you can see, pardon me, you can see it'd be very hard to add that, which is why what I did is a little bit more useful. However, you could find pure lines. So there's no pure line there, there's no pure line there, there's no pure line there. So there's really only pure lines at the first and the last dots. So this technique that I've used here is a pretty solid technique to show you when 2 lines are adding up. When it's not 2 lines, you should add up. For instance, if it's 2 squiggles, and you had to add up 2 squiggles, you would have to do a few coordinates individually because it's not following a uniform pattern. Alternatively, you could come up with the formula for this. Okay, so what is the formula? This is, let's come up with the blue line. Okay, so we're going to come up with the blue line formula. F. And right there it's 1 comma 6. So it's got 1 comma 6. And right down there it's minus 4 comma 2. So you could come up with the formula right there. I see a y-intercept is not quite clean, but let's call it 5. And I could do the slope. 6 minus 2 is 4. 1 minus 4 is 5. So I get 4 over 5 is the slope times x plus 5, and it's upward graph. And then I can do the same for this and come up with a formula for that. And then you can actually find out individual values and add them all up in Desmos. You can also add their exact formulas, which would work as well, but we'll get into that. Let's look at this. So this one as well, we're adding the thing. Let's look at the starting point. Notice this one's declining and this one's flat. So we're essentially just always subtracting the same number over and over again, which is 3. So essentially this line's just going to go down to 3 and go down like that. It's just going to be the blue line lowered by 3 because we're consistently subtracting 3 from this line. But to make sure, let's look. Minus 4 comma 3 here, minus 4 comma 5 here. What's the subtraction? 5, I should say we're going to add 3 to it. What's, because we're doing f plus g. So what's 3 plus 5? It's 8. So it's way up here. So I'm going to draw a new green line way up here. And then right here we got 4 comma 1 and 4 comma 3. And when you add them together, you get 4 comma 4. And then I can just draw a line joining those 2 dots. And sure enough, look how it's parallel to blue. And look how it's essentially not 4 above. I should have said 3 above. Because this red line is at y is equal to 3. See how it's 3 above, 3 above, 3 above, 3 above, 3 above. And the reason I know it's a line is because when you add 2 lines, they're going to become lines. When you subtract 2 lines, it's going to become a line. Okay, now they're asking you to subtract 2 lines. And this is very similar, except they're saying f minus g. So you look at this f value here. It's 5, the y value here. And the y value here is minus 2. So what's 5 minus 2? Remember, whenever they ask you to do something, that's an independent action and that's an independent unit. Don't suddenly just say 5 minus 2, because that's not accurate. So when you get 5, they're asking you to take y values and subtract y values. So 5 minus this y value becomes 5 plus 2. So you get 5 plus 2, and it's a 7. So I would put the dot right there at 7. And then right here, they share the same value, 0 minus 0 is 0. So I put the dot right there, and then I join this and that. And if in doubt, you could find out using Desmos. But you might ask yourself, how come that line went up entirely the whole way? Well, look at all the y values of g. All the y values go from 0 all the way down to minus 2. When I subtract all these values, they're all essentially minus except for the 0. Whenever I subtract a minus number, I'm going to be adding it. which explains why the line has gone above the blue line the whole way. And notice I'm adding larger and larger amounts, so the green line gets further and further apart from the blue line. And this one's the same thing. If you're going to predict it, I would say the new line's going to cross. So what's 4 minus 2? It's 2. So it's going to share it right there. And what's, notice, don't subtract those. You should be subtracting that. So that's very hard to see. But we can take a guess. This is definitely 6. And what is that there? It's about 2.5. 2.5. So what's 6 minus 2.5? It's 3.5. So right about there. And anything else they do not have in common, so you would not be drawing it. But we connect, and it didn't do what I thought it would do. When we connect it, we get that. You might logically say, why does F progressively, why does this green line progressively get further from F? And it's a good question. 6 minus 3.5, is that right? Yeah. Well, we're subtracting, oh, you know what I did wrong there? I subtracted the wrong number. So F is blue, and I was trying to figure that out right there. So F is at 2, minus 4. What's 2 minus 4? Minus 2. Okay? And the last one here, F is at 6, minus 3.5. It's 2.5. So that's what's going on. And 2.5 is almost, sorry, 3.5 is right there. And now I'm going to join them. And you might say, why is it approaching, why is that green line approaching the F line? It's because we're subtracting smaller and smaller amounts of the red line. And the blue line's getting bigger and bigger as the red line's getting smaller and smaller. So you're subtracting smaller and smaller amounts until it's actually going to pass the blue line and keep going up like that. You've got to read these things carefully, and you can see that anyone can make a mistake. Use these graphs to do the multiplier. Okay, we'll take a guess. We're going to see if we can find points that are easy to see. And so, let's see if we can spot some that are really easy. I mean, technically, I think that one's easy and that one's easy, the very end. So we got a 2, and we've got a minus 2, and when I multiply those, I get minus 4. So I'm going to go minus 4 comma minus 4 right there. And then when I go to the end, the very end here is pretty clean. I got a 8 comma 7 and an 8 comma 5. And when I multiply them, I get an 8 comma 35, way off the chart. Way off the chart. Now, here's an interesting question. What do you think the joining points are going to look like? And I will argue that since they're both increasing, we're going to get a curve. Because think about it, when you multiply a y times a y, you're going to get a y squared. Let's see if that's true. And what happens there. So to test this theory, let's just put out any positive line we want, 3x plus 3. And then we're going to put in another positive line, and we're going to make it slightly less sloped and a bit lower so that we get some minuses in it. And we're going to hit home so that we can see it a bit more clearly. And then we're going to multiply them by saying h of x is equal to f of x times g of x. And then we're going to remove this to see what happens. Oh, look at that. We get a parabola. Now ask yourself why this would be. Well, let's look at what the lines I just used as an example. And we're going to do a whole new paint so that I don't waste that one. And so if I take my y values of this graph, so my y values of this graph are indeed these, right? I'm taking the same x values, I punched it into here, and it spits out a y value, right? And then I'm taking all my y values from my second graph, here, I'm putting in the same x values that I put into the first graph, and I'm getting y values for this one. Let's call it y2. And then this is asking me to multiply my y values. So essentially, since this is a representation of this, if I expand this, what's 3 times 2? 3x times 2x? 6x squared. What's 3x times minus 4? Minus 12x. What's 3 times 2x plus 6x? And finally, what's plus 3 times minus 4? Minus 12. I can add these common terms together. I get 6x squared minus 6x minus 12. I can even factor out a 6 from all of it, and I get x squared minus x minus 2. So we can see that, or I can leave it like this. Theoretically, if I put this in a Desmos, I will get the same graph as the purple graph. And sure enough, I do. And that's taking their formulas, their y formulas, and multiplying it to figure out their new y's. And it makes perfect sense when I multiply 2 lines that I get a parabola. Just as if I multiply 3 lines, I'll get a cubic. And if I multiply 4 lines, I'll get a quartic. If I multiply 5 lines, I'll get a 5 penta, I forget. But that's a good lesson in understanding what's going on and why the values are curved. And it makes sense because as this one increases, it's increasing faster than this one because of its slope. And it'll produce negative numbers and then suddenly turn around and get positive. If you're going to do this on a graph, though, okay, let's get rid of this one too. What you would do is you would figure out the first and the last numbers. Remember, 35 is way up here. And then multiply a couple easy ones. Here's like where crosses 0 is easy because y is 0, which means you're just going to have a y value when you multiply the two things. 0 times whatever is going to be 0. So they're going to have a 0 shared right there. And then this one, if you knew the 0, would be easier. But let's just say right here you got a 1 and a 3. 3 times 1 is going to be right on the graph. So I can almost see does that make sense? Minus 2 times 2 is minus 4. Yeah. It looks like it's curving down. So the vertex is going to be somewhere up there. Let's take another one to make sure. Where's a clean? Ah, there's a clean point. They share this point at 4, so it's at 16. So 4, 16. And it's hard to see without accurate because keep in mind this dot's way up there. So it's hard to see the pure point. What would be good is to have the formula of these lines and punch them in the Desmos. Let's look at opposite slope lines. What do you think will happen when you multiply 2 opposite slope lines? Well, keep in mind it's still a line times a line. We're probably just going to have like a downward facing parabola, or this probably produces 2 positives, always an upward facing parabola. This probably produces a downward facing parabola. But let's see. So we got a 0 there, so we're going to have a 0 multiplying for the y's. 0 times anything is 0. Right there they have the same number, 3, so there's going to be a 9 there. And then we have another 0 over here, so right here it's going to be 0. So right away I can see that it's going to sort of peak at 9 and come back down here. And notice that it's going to have an x-intercept. This parabola is going to have an x-intercept wherever the x-intercepts are on either of these lines. And that's interesting because essentially that's where you would find the roots or the factors of this parabola, is right when it hits the x-axis. So it's interesting to know that what's going on is it's the 0 of one of the lines and the 0 of the other lines that creates the roots in a parabola. Okay, so that means these ones, positive lines, will make a upward facing parabola, and opposite line slopes will make a downward facing. Let's test that out. Now, this one didn't because I lowered it. No, it's an upward facing parabola. Let's make this slope negative on this line. Boom. We've got a downward facing parabola. So when you have opposite lines going in opposite, have opposite slopes, like one's negative, one's positive, you're going to have a downward facing parabola. And when they're both positive, you're going to have a positive slopes, you're going to have an upward facing parabola. And we're going to bet when they're both negative slopes, you're also going to have an upward facing parabola. Yep. So both the same slopes signs will produce upward facing parabolas, and opposites will produce downward facing parabolas. And you might say, oh, this is kind of tiny and insignificant, but the more you understand the relationships between lines, parabolas, cubics, quartics, and everything, the easier things get. Determine the equation of the new function. So essentially they're saying, okay, I want you to add them together. So it's just saying x squared plus minus x squared. What's x squared plus minus x squared? It's always obviously 0. So the common, when you add this parabola with this opposite parabola, you're going to get a horizontal line where y is equal to 0. Let's test that out. So it's saying, can you add this parabola with its opposite parabola? And let's have a look at them. What happens when we add those together? H of x is equal to f of x plus g of x. Sure enough, I get a flat line at f, y is equal to 0. And algebraically, when I take x squared and I add minus x squared, I get x squared minus x squared, which is 0. And I'm left with the formula y is equal to 0, or j of x is equal to 0. So you can see you can just add the formulas to figure out the new formula. Let's try it out with the next one in there. And let's get rid of this. Okay, now it's going to say, I want you to subtract this, where m of x is equal to that, and n of x is that. So it's essentially saying take x squared, and we're going to subtract everything in this bracket. It's very important to use your brackets, because you might just end up applying the negative just to the first term. And that would be a mistake. This negative is distributing through this, and you end up with x squared plus 7x, because minus 1 times minus 7, and then minus 12. And here you go, you have a parabola that essentially has changed. There's no point in explaining how it's changed, but that's the formula when you add it. So the important part is, when you're subtracting it, you're actually keeping a minus 1 that distributes throughout it first. It's very easy just to also think of it this way. With this minus here, all the symbols here are going to go opposite of what they are. Because it's minus, what's minus 7x? It's plus 7x. What's minus plus 12? It's minus 12. But I just like to use the distribution thing so it's sometimes clearer to students. Okay, what about this next one? In C, we're going to add two functions. We're going to add s of x and t of x, where 1 is the absolute value and 1 is 2x. Now, 2 to the power of x. So you're adding a growth curve and an absolute value curve. Both are standards, and it helps to understand a few points. We know that there's going to be 0, 1 here, and 1, 2. We know we're going to have 1, 1, and 0, whatever. So this is probably going to share this point, and then it's probably going to go up. And what happens here, it's going to affect the growth curve and start to raise it. Oh, they want us to sketch this. Okay, well, we'll use Desmos to sketch it. But one thing you could do if you wanted to sketch it by hand is take some values that you know for absolute value. So this is the absolute value of x. So x and y values. You know it's minus 2, minus 1, 0, 1, and 2 makes a y of 2, 1, 0, 1, and 2. And you know for the growth curve, 2 of x, you might want to just work on the positive side of it. No, actually negative works as well. For the growth curve, 2 to the power of x, when x is minus 2, you get a quarter. When x is minus 1, you get a half. When x is 0, you get 1. When x is 1, you get 2. When x is 2, you get 4. Now we would just add all their y values. this, minus 2. I'm going to add their y values, 2.25. Minus 1, I'm going to add all their y values, you get 1.5. Minus, or 0, I'm going to add their y values, you get 1. 1, I'm going to add their y values, you get 3. 2, I'm going to add their y values, you get 2 and 4. 2 and 4, 6. So you can see it's going to dramatically increase on this side, so it's going to be 3 plus 8, 11. Okay, it's going to go up and up and up. And then on this side, you can see that it goes down and then starts to climb again. So that absolute value is going to start making my growth curve climb again. Let's have a look. So if I look at f of x and call it the absolute value of x, and then I look at g of x and I call it 2 to the power of x, okay, notice my growth curve. It starts small, small, small and goes up, skyrockets. Notice my absolute value goes down, 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 and then up, up, up. So I have these little tiny values of growth curve, and I'm adding these massive values of of absolute value. So I'm going to eventually start looking like a normal absolute value, especially as my growth numbers become insignificant. And over here, I'm just going to grow it incredibly rapidly. So essentially, I'm predicting that it will look like this. It's going to, on this side, really skyrocket, and this side it's going to sort of look like a growth curve, and then it's going to start looking like a normal absolute value line. Let's have a look. Yeah. Notice as I zoom out, it's looking almost exactly like an absolute value curve, and that's because the tiny numbers of growth curve no longer have an impact. And then over here, if I look on the right, I can see that it is growing much faster than a growth curve. And you might say, oh, why is it getting closer and closer? And that's because the growth curve numbers are so much bigger than the absolute value numbers that it's essentially becoming a growth curve. So essentially the right side of origin is going to look like the growth curve, and the left side of origin is going to look like the absolute value curve, and that's because their y values overwhelm the other curve. Good way to think of it, overwhelms the other curve. But also notice it's nowhere near the y-axis anymore. The lowest point is going to be right there. And that's where the absolute value curve has a 0, 0 coordinate. So we just end up using the growth coordinate. So it's good to predict, good to understand what's going on. Okay. Then they're asking us to multiply an x times an x squared. What do you think is going to happen when I multiply an x and an x squared? Well, what is x times x squared? The rule says when the bases are the same, we add their exponents. 2 plus 1, x to the power 3. So we're going to have a graph. So when I add a line and a parabola, when I multiply, product them, I'm going to be left with a cubic. A cubic. And algebraically, it makes sense. What essentially is happening? Well, as my line values get more and more, especially into the negative, once it crosses origin, remember here, okay, let's draw this parabola and this line more accurately. Here's my parabola. It goes through 0, 0, and so does my line. So what happens when my line is suddenly in the negative zone here? Multiplying these positive numbers, it suddenly turns all the y values positive. And that's why it looked like a normal parabola on the right side and a flipped image parabola on the left side, flipped in the x-axis. So let's have a look. So there's my line. See, notice all my left of the origin, all my y values are negative. Right? And then I'm going to look at my normal parabola. Right? All my values are positive except at origin, which means we're going to share this origin point when I multiply them. And here's the multiplier. It's the same as a cubic. And it's sure enough, on the left side, all of a sudden I look like a parabola that's reflected in the x-axis because all my y coordinates from the line are negative, and they're multiplying the positive coordinates from the parabola, creating negative coordinates. And then finally, oh, that's it. Using the graphs you sketched in question 5, compare and contrast the relationship between the properties of the original function and the properties of the new function. Fair enough. We kind of did that. These nullified one another. This one created a parabola that we should actually look at that. When I subtract, let's look at that line and try to understand what's going on. 7x plus 12. And I'm not going to be multiplying them. So here we have a line that becomes negative after 1.74, which means if I have a parabola there, and I'll keep them both up, right there, let's do x is equal to 1.74 to see it clearly. Okay, right there, that means all my y's from, oh, and I'm subtracting. Okay, so if I was multiplying, we'd see a sudden flip down into the negative zone. Because I'm subtracting this from that, okay, that means this is overwhelming this line. It's going to stay the same. But right probably at this point, wherever they're equal, I believe the line is going, yeah, especially here, the line is going to overwhelm it. So it's going to drag the whole thing down. I believe it's still going to be a parabola that just is dragged downwards. Yep, dragged downwards and to the left. Interesting. And that's probably because the line is, when I subtract it, I'm subtracting huge values of y, dragging the whole thing. Why would the x value? It's hard to visualize. But I want you to notice something here. When the parabola goes from negative to positive, right, the y values of my parabola become bigger than the line values. That's why it suddenly goes positive. Same with this side. Right here, the line values are bigger than my parabola y values, and right here, the y values of the parabola are bigger than my line values. And that's why between this and this, I am in the negative zone, because that's where my line y values are much bigger than my parabola values, especially as my parabola approaches 0. Hard to comprehend that sentence, but that's okay. And this one, what's going on when we're adding it? Well, we're just, as I pointed out, we're pretty much overwhelming one graph with the other graph. And what's going on with that? We're just creating a cubic. This helps to understand, because when we get into calculus, we kind of go backwards on this, and it'll help you understand where all the calculus comes from. Okay, we're given a line and we're giving a downward facing parabola. Sketch each, make a table of values for when we multiply them. Use the table to sketch. Okay, let's keep this one honest, because they want you to practice. The reason they want you to practice this is so that you understand what a computer is doing, or understand what a model looks like, or what like if you're studying data and you're trying to understand why some data suddenly switched around, understanding these basic models will help you. So we're going to do a line, and I'm going to do a rough graph. So what's the first one? It's x plus 3, right? So we know that that's going to go through origin here at 3, 0, 3, and it's just going to go down by 1 each time. So it's going to have another one here at minus 3 comma 0. And there we go. And it's also going to have a 4 comma 1, a 5 comma 2, a 6 comma 3. And if you don't understand how I got those, then go practice your lines more. You can see I got these dots a little bit off from a straight line. But anyway, the minus 3 is the only important one, and the 3 is the only important one. So I got a 6, comma 3, and a minus 3, comma 0. And then this one is a downward facing parabola at the coordinates 0, comma 5. So right here in red, 0, comma 5, 1, 2, right there. And it's only going to go down 1 here, so it's going to share that dot right there. And then it's going to go down even more to here. And more to here. And there's a and where does it cross the x-axis? We'd have to factor it. Let's factor out negative 1. I get x squared plus 5. And then when I factor out negative 1, in fact, I can't factor out an x. Oh, I get x minus 5, sorry. So essentially be x plus square root of 5 and x minus square root of 5. Try to figure out how I came up with that one. Because they're essentially a difference of two squares, and I just created my own square. That's all. So that means that's going to be the roots, which means it's going to go through 0, comma square root of 5 and, or sorry, square root of 5, comma 0, and negative square root of 5, comma 0. But you don't get accurate values for that, so the best thing you can do is make a chart for this. And since they want minus 3 all the way up to positive 3, you might as well take x values of minus 3. What's minus 3 squared? 9. Multiplied by minus 1. Minus 9 plus 5. Minus 4. Minus 2 squared? 4. Times minus 1. Minus 4 plus 5 plus 1. Minus 1 squared? Positive 1 times minus 1. Minus 1 plus 5 plus 4. 0 squared plus 5. 1 squared minus 1. And now these will start to repeat. 1, and there's one going to be one last one. 3, 3, comma, minus 4. So now you have 3 values for that. If I'm going to do the other one, I have these values for the same thing. Minus 3, comma 0, minus 2, comma 1, minus 1, comma 2, 0, comma 3, 1, comma 4, 2, comma 5, and 3, comma 6. Okay, good enough. And then they're asking us to where's the h of x? Multiply them. So you just take their y values and you multiply them. So in my new graph, I'm going to get this. What do you think a parabola times a line is going to create? It's going to create a cubic. So at minus 3, multiply minus 3, multiply the minus 4 and the 0, I get 0. At minus 2, multiply the 1 and the 1, I get 1. Minus 1, multiply the 2 and the 4, I get 8. 0, I get 3 times 5, 15. At 1, I get 4 times 4, 16. At 2, I get 1 times 5, 5. And at 3, I get 6 times minus 4, which is minus 24. Is that right for the 3? 9 minus 9 plus 5 minus 4. Yep. Yep, there we go. So if I graph my new blue dots, I get minus 3 comma 0. Notice they share the same dot. That's because there's a 0 there. We're also going to share the same dot at square root of 5. Minus 2 comma 1. Minus 2 comma 1. Minus 1 comma 8. So it's going to jump up. 0 comma 15 way up here. 1 comma 16, a little bit higher. 3 comma negative 24. Boy, it really jumped down there. there's going to be a turnaround point somewhere. Probably like that. Let's see. So we're going to take f of x. We're going to do minus x squared plus 5. If you want to see what that looks like when it's correctly factored, it's minus x squared minus 5. And we're going to do the line x plus 3. Okay. Get rid of that, get rid of that. So there's our two lines, sure enough, with all the points. And believe it or not, if you go here, what's the square root of 5? 2.236. Did I get it? Yes, I did. And so that means what happens when we multiply these things? And I'll make it a different color. Boom. I'll turn off them. Of course, you're going to get a cubic. It's inverted because of this minus. So it starts in quadrant 2 and ends in quadrant 4. Sure enough, they're going to share the same dot at both the square root. That's something I should have figured out. They're going to share the same dot at 0 at square root and at minus 3, and then again at the positive square root, because that's where the parabola and the lines all cross the x-intercept. So there's something to note. Where the line cross and where the parabola cross, the x-intercept creates the 3 intercept points of this cubic. And since we're only doing the range from minus 3, smaller equal to x, smaller equal to 3, and we're doing the same range for the other one, you end up with this. Sure enough, look. There's the y-intercept we had. And there's that other one. And it goes down as far as there. Like I said, minus 24. The only thing we didn't, and I should have predicted, was this little turnaround point there, because I should have realized the 3 intercept points would be the square root of 5, the negative square root of 5, and the negative 3 of the line. So interesting. And when you have a cubic, if it goes through the x-intercept twice, it had to turn around somewhere, because cubics are always the same pattern. Determine the algebraic model. Okay. That would just be multiplying. Oh, sorry, I'm on the wrong one. That would just be multiplying this times that. So if I take this and put it in brackets and multiply it by that, and put it in brackets, and then you just distribute it. Okay. Okay. What's x times negative x squared? Negative x cubed. What's x times 5? Plus 5x. What's plus 3 times minus x squared? Minus 3x squared. And then finally, what's plus 3 times plus 5? Plus 15. So I'm left with the algebraic model of, and always put your terms in the right order, minus x cubed minus 3x squared plus 5x plus 15. So I got to put on my squares in there, cube, squared, and just x. And then you could leave it like that if you wanted. So if I write this down, I should get the same as h of x. What did I get? Oh, I didn't have the equals in there. I don't think I got the right thing. X cubed minus 3x squared plus 5x, not minus 5x. And there you go. My purple and my red line matches perfectly. So this is the Desmos doing it, and this is our algebraic expansion. And then they ask you to do it again with a parabola and a parabola. So if I multiply a parabola, let's see if we can predict this, okay? We'll just do this. I'm just going to make it bigger and crop it. So looking at that, let's look at this first parabola here. What's x squared minus 2? It's an upward facing parabola that has the vertex 0, comma, minus 2, which probably means it's going to cross the, if I were to factor that, I would get x plus the square root of 2 and x minus the square root of 2. And then the other one is x squared plus 2, which you can't really factor, but it has a vertex of 0, comma 2, and it faces up. They both face up. So they're essentially just parabolas that are raised and they're lowered. So that other one that is x plus 2 doesn't have a root. It doesn't have an x-intercept. It doesn't have a 0. So that means the only zeros we're going to have are at these points. Now, they're asking you to do the same thing, and you can go ahead and do that, and just know that they're going to have the same values as a parabola, but one's subtracted and one's adding to. So if you're going to do it for x squared plus 2, when x is that, it's going to get 9 plus 2, 11. When that's minus 2 squared, you're going to get 4 plus 2, 6. For minus 1 squared, you're going to get 1 plus 2, 3. For 0, you're going to get 2. There's his. And then it's going to repeat. Because it's symmetrical. And this time we're multiplying it. First of all, when you're multiplying an x squared and a parabola and a parabola, you're going to end up with x to the 4, a cubic. So there's that answer to that one. What's the degree? And then the other one, if I look at its xy values, I'll just do a line, is going to be very similar. This time we're going to subtract 2. So instead of, it's going to be 9 . God damn. 9 minus 2, 7. So all the values are just going to be down by 4. Minus 1 squared, 1 minus 2, so minus 1. See, all the values are down by 4. And then they repeat. Okay, and then if you multiply these, and we'll just call this green, you're going to get x values that are like this. Minus 3, 11. Or sorry, 11 times 7, 77. Minus 2, 6 times 2, 12. Minus 3, sorry, minus 1. 3 times minus 1, minus 3. So we're into the negative now. At 0, we're going to get minus 4. At 1, we're going to get minus 4 again. I'm just multiplying all the y values. At 2, we're going to get 12. Repeats. 3, we're going to get. It doesn't quite repeat. Yeah, it does. 77. Because the numbers repeat, the multipliers are going to repeat as well. Notice something interesting here happens at 0, though. It's no longer the vertex. Let's see if we can figure out what's going on here and predict what the drawing is going to look like. So if I'm going to plot some points here, minus 3 is going to be minus 11. Sorry, 77, way up here. Minus 2 is going to be 12, so it's going to do a steep dive. Minus 1 is going to dive down to minus 3. 0 is going to be minus 4. 1 is going to be minus 4. 2 is going to be 12 again. 3 is going to be 7, 7. So notice there's this axis of symmetry right here at a half. And x is equal to half. right in between. And that's, you can notice that between 0 and -4. Now also notice it's going to cross the line here at the x-axis, and my prediction is it's going to cross at minus square root of 2 comma 0 and square root of 2 comma 0. So it's going to cross right here. And you might even have a little bump here, whereas it's going to come down and create a little w up and down. And it takes more advanced calculus to show that's going to happen. It also might just be flat, but I'm going to predict it's going to have a little bump between 0 and 1, and the peak here is going to be at 1/2 of x. And I don't know what the peak's going to be, except that it's going to be below the x-axis, because it can't cross the x-axis more than twice. Let's have a look. Keep the same domain. Okay, let's turn that off. So there's the first parabola, there's the second parabola, and here's the multiplier. Let's get rid of them. Notice the multiplier crosses at the same x-intercepts as the red, because the red's the only one that crosses the x-intercept. And, oh, no, it did not do a little w bump, it flattened out. But let's put a line x is equal to 0.5. Oh, it didn't do it. So I had some calculation errors there. Because at 1 it's not -4. So I did some multiplying errors. Let's see if I can spot what it was. So it's -3. Oh, right there. 1 is -3. The rest is fine. Yeah, because it's got a match. So that means the vertex is right there. Which makes sense. Well, I don't know what I was thinking there, because you can't have... You see how they both have symmetry around the y-axis? Which means their product is also going to have symmetry perfectly around the y-axis. You couldn't have it any other way. And that's what it looks like. Notice the peak up here, 77. 77. Now I want to more interestingly point out the intercepts. They're going to be the square root of 2. 1.414 and -1.14 are indeed the square root of 2. There you go. So this is called a cubic, and you can't quite see it because their adjustments are perfect. There is a way of making it a W, and I was just trying to show how, but I failed. Yeah, I did fail badly. Yeah, still didn't do it. Anyway, we'll get into how to show W's. Most cubics don't look like parent cubics look that good, but most cubics look like this. Did it do it? No, it didn't. Let's see if that'll do it. Oh, almost. You're usually going to have a little turning point like that, like a W. A good one would be to do it like this. X minus 4, X minus 2, X plus 2, X plus 4. There, we're going to see a nice W here. There. And put a 0.3 to give it more of a W shape. Yeah, there we go. That's what you'll see a lot of cubics, and they sometimes cross the x-axis up to 4 times maximum. We'll get into the rules about cubics later. This entire chapter is just trying to help you understand what you're dealing with, essentially. And that's it. That was a long thing for what's seemingly a simple chapter. But the more you understand these graphs and how they interact, the more you'll understand modeling and science in general and how to interpret data, graphs, and what's going on.